Hello everyone, and welcome to this seminar on distributed ledger technologies. So in this seminar, we are planning to dive deep in some of the essential concepts related to the distributed ledger technologies, or DLT. So as you can see in this agenda, so we're gonna quickly cover some of the fundamentals and some of the key concepts that you need to know. Then we will cover some of these key architecture patterns that we have for distributed ledger technology. And then we will cover the concepts like smart contracts on some of the essential platforms like Ethereum to build DLT for businesses. All right, let's start with this essential, I would say, fundamental. So what we are looking at here is a major transformation in how transactional data is handled across networks. So classically, most of the businesses and companies relied on central authorities like banks, corporation, or government bodies to manage, verify, and store data. They were the single source of truth, and trust was placed in them to maintain the integrity of those data. But the distributed ledger technology, or DLT, flips the model. So instead of one central authority, trust is now shared across a network. Through cryptographic mechanism, participants in the network collectively maintain and agree on the state of the data. This shift from centralized control to distributed trust removed this single point of failure and opened the doors for more transparent, resilient, and collaborative systems. So as some of you may know, like DLT is actually the foundation of the next generation of web, or Web 3. Now let's talk about some of these key components of the DLT. So firstly, we have peer-to-peer networking, which is the foundation of distributed ledger technology. So instead of relying on a central server like a database, DLT is based on peer-to-peer networking, which means data is exchanged directly between nodes. So these are the participants in the network. So these setups allows for decentralized data exchange and also ensure the system can synchronize its state across all nodes even without a central authority. So as you can see, like let's say if you have a bank account, so like the bank is actually just taking care of all the database servers and making sure all your transactional data is stored and saved. But then in the DLT, all these components, even your device that you use to access to your bank account, it can be like a node, and then it can have do this peer-to-peer networking with all other nodes across the network. The second component is the cryptographic structure. This is actually just to ensure the integrity of the data. So each piece of data is hashed and linked to the one before. So these actually form a secure chain that is tamper resistant. So any attempt to alter the data would break these links, making tampering immediately obvious to the network. And then finally, we have the consensus mechanism. So the consensus mechanism are those rules and processes that network use to reach collective agreements on what's true. So rather than trusting a central entity, the network participants validate transaction together. And this is actually what builds trust in the decentralized environment. Now let's dive deep in each of these components. Let's start with the P2P. So in P2P networking, the first step is the transaction propagation. So whenever a new transaction is created, it needs to be quickly broadcast across all nodes in the network. This rapid mechanism ensures that every participant is working from the same up-to-date information, which is essential before the network can move to the consensus. Then we have the utility functions, which are responsible for protecting both the integrity and also the confidentiality of the data as it moves through the network. So these functions, often powered by cryptographic techniques, make sure that data cannot be altered or intercepted during the transfer. Then we have the storage management. So since data is stored across many nodes, the system has to carefully balance how much data is replicated and how to do so securely, all while managing costs and complying with data protection standards. And finally, we have node management, so which ensures that each node behaves according to protocol, manage resources efficiently, and also remain synchronized with the rest of the network. This is vital to maintaining the overall integrity and also reliability of the ledger. So these are like the key component of the P2P network for the DLT. Now let's go to next one, which is the consensus, which is the heart of any DLT. It's what allows a network of independent nodes to agree on a single shared version of the truth without needing a central authority. So for consensus, we have these validation rules. These are the predefined criteria that determine whether a transaction is legitimate. Each node checks new transaction against these rules. Think of them as a built-in checklist for what's acceptable. Next, we have data consistency algorithms. So these are actually ensure that all nodes end up with the same view of the ledger. Even as data flows in from multiple sources, these algorithms work to maintain a uniform, synchronized state across the network. And finally, we have the distribution and synchronization processes, which make sure that once consensus is reached, the agreed upon data is consistently and accurately propagated to every node. This coordination is what gives the network its reliability and also the integrity. So consensus here is not just about agreeing, it's all about doing it in a structured, verifiable way that keeps the entire system aligned and also trustworthy. Now let's talk about one of these famous one of those consensus, Nakamoto consensus, which referred to the family of consensus mechanism inspired by Bitcoin's original design, and it includes two major approaches, proof of work and proof of stake. So starting with proof of work, or POW, this is the original mechanism behind Bitcoin. So it relies on miners solving complex mathematical problems to validate transaction. The system is extremely secure and highly decentralized because anyone with computing power can participate. However, it actually comes with a trade-off. It's very energy intensive, and also has a slower transaction speed and doesn't scale easily as the network grows. To deal with some of these POW challenges, we have proof of stake, or POS, which replaces the energy-heavy mining process with a model based on ownership or a stake in the network. Validators are chosen to propose and confirm block based on how much they've staked. This makes POS for far more energy efficient and also significantly improve the scalability. It also introduced an economic security model where validators have some things to lose, helping to keep them honest. All right, now let's talk about the BFT, which is a fundamental challenge, which I actually address a fundamental challenge in distributed system. So how to reach agreement even when some participant may be unreliable or malicious. It's especially powerful in the permissions or networks where speed and rapid finality are crucial. Modern BFT protocols often use innovative technique like gossip about gossip, which is more around like that the nodes don't just share transaction, they are also share information about who else has seen what. Over time, this creates a rich, verifiable history of communication, helping the network build the consensus more efficiently. Then there is a virtual voting. Instead of actually sending vote over network, each node can mathematically deduce how others would have voted based on shared information. This actually cut down on communication overhead and also speed of the decision making. The result is rapid finality, meaning once a decision is made, it's final and irreversible. All right. Now let's talk about the trust model. So the growing intersection between technology and organizational governance in distributed system, like it's a challenge, right? When you're distributing everything, the governance model is going to be challenged, because then you don't have like a central authority to address all those governance concerns. So we have this technical trust, which is in the DLT model, is established through the protocol. So specifically through the consensus mechanism. It ensures that the system behaves as expected, the data is accurate, and also that no single party can manipulate the outcomes. In the real world application, especially in the enterprise, institutional trust is also equally important. That's where governance, compliance, and also account or right management comes into play. These elements define who can do what, under which rules, and also how disputes are resolved, all layers into the protocol. In this way, the consensus algorithm becomes more than a technical tool. It actually serves a machine enforceable version of the contractual agreements among the participants. It actually codifies shared rules and also trust into the fabric of the system, aligning both technical integrity and also organizational accountability. Now let's talk about the data structures. So there are like the underlying data structure for the DLT. There are like two main types of data structure. We have the linear blockchain and also directed acyclic graph, or DAG. So linear blockchain like Bitcoin or Ethereum organize data into a single sequential chain of block. Each block links to the one before, creating a clear auditable history. This structure offers strong security and decentralization, but it actually comes with limitation, primarily speed, because only one block is created at a time, and transaction throughput tends to be very low, typically around 5 to 15 transactions per second. In contrast, we have the DAG-based system, which use a non-linear structure, where multiple transactions or events can be processed in parallel. This allows for much higher throughput, faster confirmation times, and also offer lower operation cost. It's a great fit for applications that need speed and scale without significantly without sacrificing data integrity. One notable example is Hashgraph, which is a used DAG system. So it actually delivers high performance and also strong security. The main kind of features of those are the virtual voting and gossip protocol that can help to achieve these performance. However, it's governed by a limited group up to 39 corporations, which includes a degree of centralization. So in summary, while blockchain emphasizes security and simplicity, DAG focuses on speed and scalability. And as we mentioned, each has its own trade-off. Let's talk about the blockchain architecture, which is built around a simple but powerful concept. Data is stored in block, and each block is cryptographically linked to the one before. This actually created immutable tamper-evident chain of record, which is ideal for ensuring data integrity and trust across a decentralized network. This design is what gives blockchain like Bitcoin and the original Ethereum the strong security and also relationship to censorship. However, as we mentioned, the sequential nature of blockchain means that the transaction can only be added one block at a time. We already covered some of these, but this is actually the main bottleneck for the blockchain. And then for the DAG system, also, as we mentioned, it actually just take a very different approach from traditional classic blockchain. And instead of bundling transaction into block, it actually each individual transaction reference one or more previous transactions directly. This structure actually removes the need for sequential block creation and allows multiple transactions to be processed at the same time. So there is a lot of faster consensus and also improved scalability here. However, again, DAG often operate with small node counts, especially in early or permissioned deployment. That can pose a challenge when it comes to maintaining the same level of security and decentralization seen in more mature blockchain network. All right, so let's talk about the some comparison for some of these decentralized platforms. So on the left, we have Ethereum, which boasted around 4,500 active nodes distributed across the globe. These nodes are run by individuals, organizations, and validators who independently maintain the network. As we mentioned, Ethereum is based on blockchain, right? And this widespread participation ensures broad decentralization, making the network more resilient and also difficult to control. In contrast, Hedera, which is based on DAG, is governed by a council of 39 well-known corporations. While this model allows for faster performance and also more predictable decision-making, it also introduces a more centralized architecture structure, which is, it's more like classic types of model, right? So while Hedera may excel in speed and efficiency, Ethereum emphasizes on openness and also distribution. All right, now let's talk about the trust model. So we have two types of system when it comes to the DLT. We have permissionless and also permissions. So permissionless DLT, like Bitcoin and Ethereum, are open to anyone. Anyone can join, validate transaction, and deploy application without needing approval. This model actually prioritizes decentralized transparency and also censorship resistance. On the other hand, we have permission DLT, which restrict participants to authorize to those entities with authority, typically through formal onboarding with identity verification like KYC or KYB. KYC is like know your customer, or KYB. This is like just a authorization model. KYB is know your business. This network offers granular access control and optional transparency, which makes them well suited for regulated industries such as finance, healthcare, or supply chain. So permissionless system focus on openness and resilience, while permission networks are optimal for control, compliance, and collaboration among known participants. Performance trade-off, again, like any other system, we have trade-off. Permissionless network prioritizes decentralization, as we already mentioned, and openness, which means including thousands of validators, while this enhances trust and security, but it actually slows things down. In contrast, permission network are built for speed and efficiency because they have a smaller set of known vetted validators. They can process transaction much faster, and this can make them ideal for use cases where performance is critical, especially like things in financial clearing or enterprise data exchange. All right, let's quickly also touch on the transaction lifecycle for DLT system. So it all begins with the initiation and signing. So a user creates a transaction and signing it using their private key. This cryptographic signature ensures non-reputation, meaning the sender cannot deny having sent it, and that transaction authenticity can be independently verified. Next, we have network propagation. The signed transaction is broadcasted to all nodes of the network. This ensures everyone has visibility into the transaction and is prepared to validate it. Then we move to the independent validation. Each node checks the transaction against the protocol rules, verifying things like digital signature, account balance, and transaction format. And only valid transactions are kept and forwarded. Once the transaction passes the validation, it enters to the consensus agreement phase. The network collectively agree on whether the transaction should be added to the ledger, and this might involve things like proof of work, proof of stake, or those types of consensus mechanism. Finally, the transaction is immutably recorded. It's added to the ledger in a tamper-proof way, whether in a block or a DAG structure, create a permanent transparent record that can be audited by anyone with access to the network. Let's touch on the concept of immutability in more details, which is one of the most powerful features of the DLT, which guarantees that once the data is added to the ledger through the consensus, it cannot be altered or deleted. This isn't just a technical feature, it's actually a critical operational and legal asset. Immutability ensures non-repudiation, which means parties cannot later deny the validity of the recorded transaction. This is actually especially valuable in regulated sectors such as post-trade processes of securities. Here, immutable records enhance auditability, reduce reconciliation need, and also support straight through processing. Automating transactions flows from start to finish with minimal manual intervention. This results not only in greater efficiency but also stronger compliance and reduced risk. All right, now let's talk about the smart contract, which are essentially self-executing code that lives on a distributed ledger. They form the programmable logic layer of the DLT, enabling automation, trustless interaction, and also customized business logic without those intermediary. But the function securely and also reliably, they need a careful control execution environment. Before we continue, if you see the flow of all these slides that we went through, we start with the foundation, which is usually layer 1, which is all those concept of networking, consensus mechanism, P2P network. That's the layer 1. Then in the layer 2 is more on the data structure that we use, whether it's a blockchain or that. And then a smart contract, which is the logic layer, is actually layer 3 of the DLT system. And then layer 4 is the application. These are like the 4 fundamental layers. And layer 3, as I mentioned, is a smart contract. So, like as an example, we have this Ethereum virtual machine, or EVM, which is a decentralized, globally distributed computation engine that ensures smart contracts are executed deterministically. So if you want to run any of those smart contracts, you can use like some of these EVM, which means every node reaches to the same outcome when processing the same output. This is one of the key features of smart contract, that it's deterministic. To maintain security, the EVM uses a sandbox environment. This means smart contracts are isolated from the underlying operating system, preventing them from causing unintended effect or accessing unauthorized resources. Finally, EVM, we have this concept of gas mechanism. Every operation smart contract performed has a cost paid in gas. This serves 2 key purposes. It multiplies computation to prevent abuse, like denial of service attack, and also incentivize validators to process transaction and maintain the network. Together, these elements create a secure, efficient, and also predictable foundation for decentralized application logic. Let's talk about this EVM in some more details. So EVM doesn't just power Ethereum, it's actually become a de facto standard across much of the blockchain ecosystem. This standardization plays a crucial role in promoting interoperability, because many blockchains like Polygon, Avalanche, and Binance Smart Chain are EVM compatible. The same smart contract code can be deployed across all of them. That means developer can write code once and run it on multiple platforms without rewriting or redesigning for each chain. So like if you want to develop, as an example, a smart contract based on your use case, so EVM would be like a kind of standardized way of doing that. This can actually reduce development complexity and foster a consistent ecosystem of tools, libraries, and best practices. It also ensures predictable behavior, which is crucial when deploying financial logic or mission-critical application across different environments. In short, EVM standardization is a key driver of ecosystem growth, developer efficiency, and also cross-chain functionalities. Some more details about the smart contract. While smart contracts bring automation and trustless execution, their immutability is a double-edged sword. Once a contract is deployed, its code cannot be changed, which means any bugs or vulnerabilities become permanent and can result in irreversible financial loss. So some of the critical risks, we have reentrancy attack exploit which exploit the timing of the contract execution. An attacker can repeatedly call a function before the contract updates its state, potentially draining fund. And this was famously seen in the DAO hack on Ethereum. Integer or overflow or underflow happen when numerical values exceeded their limits, causing them to wrap around, either resetting to 0 or another unintended value. This can corrupt contract logic and also allow manipulation. Flash loan attacks are a new version of those risks, sophisticated one. Here, attackers borrow large amount of capital without collateral, exploit a contract vulnerabilities within a single transaction, and repay the loan, keeping an extracted profit. It's fast, difficult to detect, and also highly damaging. Lastly, we have the denial of service attack, target the availability of the smart contract by exhausting gas limit or computational resources. Attacker can make contract unusable, effectively freezing their functionality. These risks highlight why rigorous auditability, formal verification, and also secure coding practice are essential when deploying smart contract in any high-stake environment. Now let's talk about how we can bridge on-chain and off-chain data. Smart contracts are powerful, but by design they are deterministic and closed system, meaning they cannot access data outside the blockchain on their own. To interact with the real world, like market prices, weather data, or shipment update, they need a trusted connection to off-chain information. That's where oracles actually come in. The process starts with the data source. This could be anything from web API or IoT device to the traditional database. Next, we have Oracle middleware, which acts as a secure bridge. It collects external data and translates it into format that a smart contract can understand. Before the data is used, it goes through cryptographic verification to ensure it's accurate, untampered, and also delivered on time, which is very crucial, this step. And finally, the verified data reach the blockchain, triggering on-chain integration, whether it activates smart contract function, settle agreement, or initiate other predefined action. Also, let's talk about some of these concepts of which are, I would say, very important to understand. We have zero knowledge proofs. So by default, the DLT are transparent, which is great for trust, but can be a problem when privacy is required, right? Especially in security sectors like finance, healthcare, or identity management. This is where the zero knowledge proof, or ZKPS, comes in. ZKP allows one party called the prover to demonstrate that they know or have verified certain information like a password, balance, or identity without revealing those information. The prover used that secret information known as a witness to generate a cryptographic proof. That proof is then sent to the verifier, who check its validity, and then the verifier can be fully convinced that the statement is true, and also yet they gain no access to the underlying sensitive data. In essence, ZKP provide a powerful way to reconcile transparency with confidentiality, enabling data to be verified on-chain without ever exposing them. This makes them a foundational tool for privacy-preserving blockchain application. So now let's talk about the application of those. So it's actually unlocking a new layer of privacy and confidentiality blockchain system, especially in use cases where data must be verified without being exposed. Under privacy use cases, ZKP allows users to prove they have sufficient funds without revealing their actual balance. Similarly, they can verify identity credential like age or citizenship without disclosing personal information. This is crucial for compliance. There are two main types of ZKP. We have interactive one, which involves an ongoing exchange between the prover and the verifier, where multiple rounds of communication are required. We have also a non-interactive one, which produces a single proof that can be verified by anyone, anywhere, without needing further interaction with the prover. All right, now before we finish, let's quickly jump on some platform comparison. So we have key types of platform: Ethereum, Hyperledger Fabric, Corda, Ethereum, Avalanche. These are some of the main DLT platform. So Ethereum, permissionless, using an account-based model, and the EVM, where smart contracts are typically written in Solidity. It relies on proof of stake for consensus, and also it's widely used in DeFi and Open dApp ecosystem. Hyperledger Fabric, we have a lucky slide on that one, but then it's permission one. Enterprise focus, it also uses an account-based state model but run a smart contract as chain code, typically written in Go. Its consensus is based on PBFD variant, making it suitable for supply chain and also enterprise workload. Corda, take actually a unique approach with UTXO-like state model and Corda apps written in Kotlin. It does not use traditional consensus algorithm, but instead rely on notary service to validate transaction. This structure makes Corda ideal for financial services. Hedera use a council governance trust model. We already talked about that with an EVM compatible architecture and the hash graph consensus algorithm, which provide asynchronous Byzantine fault tolerance or ABFT. It targets enterprise transaction with high performance and low latency. Avalanche, which is a permissionless one with the account-based model and full EVM compatibility. It uses its own Avalanche consensus protocol, which support high throughput and flexible subnet configuration. So as you can see, each platform here reflects a different balance of trust, performance, scalability, and governance, and which need to be tailored to the target use cases. But those top two is, I would say, the one which are more popular one. Let's quickly touch on Hyperledger Fabric architecture, which is in terms of architecture is modular permission blockchain platform, especially for enterprise use cases. One of its key features is chain code execution. Chain code, Fabric's term for a smart contract, is executed deterministically by selected endorsing peers, each running the code in an isolated containers. This setup ensures both security and consistency across organization. Fabric also uses endorsement policies, which defines who must sign off on a transaction before it's actually added to the ledger. These policies require cryptographic signatures from specified participants, giving those fine-grained control over who can validate and approve ledger chain. Overall, Fabric is designed to support strict governance, confidentiality, and compliance, making it well-suited for regulated industries like supply chain, healthcare, and finance. Corda, developed by R3, which is a privacy-first distributed ledger platform designed especially for financial industry. At the heart is the concept of global logical ledger. While it appears unified, in reality, each participant only sees the data relevant to their transaction. This approach actually ensures confidentiality and compliance. Corda also uses the UTXO-like state object. We already covered that, which represent asset or obligations that are consumed and are replaced in each transaction. This model supports efficient parallel processing, especially useful for handling complex financial instrument or high throughput token-to-token transfer. In short, Corda delivers a platform where privacy, precision, and performance comes together, tailored to the specific needs of institution managing sensitive, high-value financial transaction. Avalanche, which is also high-performance modular blockchain platform designed to deliver speed, flexibility, and scalability, is a structure actually around 3 core chains. The C chain, which is fully EVM compatible, allowing developer to deploy existing Ethereum DApp with a faster finality and also lower fees. The X chain uses a DAG optimized mechanism, making it ideal for creating and exchanging digital asset. The P chain, which handles network coordination, and it actually manages validation, staking, and most important is subnet creation. Subnets are one of the Avalanche standout feature. They enables the creation of custom layer 1 blockchain with their own rules consensus module. In summary, Avalanche combines modular architecture with cutting-edge consensus to support a diverse, scalable, and also customizable blockchain ecosystem. All right, quickly, let's talk about some of these concepts of tokenization before we close the session. So the tokenization is actually becoming a foundational strategy for modernizing capital market by representing traditional financial assets like bonds, security, and money market instrument as a digital token. on a distributed ledger. Institution can enable faster settlement, greater efficiency, and also asset fractionalization. This process typically occurs on permission platform, where compliance is essential. Things like Corda or custom Avalanche subnets are well suited here, as they enforce KYC AML requirement and provide the privacy and also control needed in regulated environments. However, tokenization still face real-world challenges, including market fragmentation, the complexity of integration with legacy financial system, and also ongoing regulatory uncertainty. Overcoming these hurdles will be the key to unlocking the full potential of DLT in transforming asset, insurance, trading, and also settlement. And the last slide, what we are seeing in the trend, central banks are actually exploring DLT-based solution to modernize the settlement of the transaction using central bank money. As part of this effort, 3 key models are being piloted to bridge the gap between distributed ledger and also traditional system. So we have full DLT interoperability. So in this model, central bank money is natively issued and settled on a DLT platform, which means the institution can hold and transfer funds within a blockchain-based environment. This actually offers a very end-to-end automation and atomic settlement, but requires major change to existing infrastructure. The TIPS hashlink, which approach integrate DLT platform with the Eurosystem's TIPS payment service via a cryptographic hashlink mechanism. Settlement still occurs in the traditional system, but its security coordinated with DLT activities, maintaining continuity and also with the existing layer. And then the third model is trigger solution. Here, a DLT-based smart contract initiates settlement externally through the API, typically in a central bank RTGS system. These models allow DLT platform to interoperate with current infrastructure without requiring full integration, making it a more flexible transitional option. This model actually reflects a range of strategies, not about just central bank, even like any other enterprises who is going to just leverage DLT, they can just go through any of these options. So of course, I think the third option would be much, I would say, reliable, and then slowly move to the option 2 and then option 1. Awesome. That was it. Let's quickly just wrap up. So we talk about some of the key concepts related to the DLT. We talk about all these different layers within the DLT. Layer 1, which is all those networking consensus, P2P communication. Layer 2, which was the data layer, including the blockchain or DAX system. Layer 3, the logic layer, which was all about the smart contract. And then layer 4, the application that we already touched. And also compare some of those key platforms like Ethereum, things like Hyperledger Fabric and Avalanche. And we talk about some of those use cases for these types of platforms. Awesome. I hope you enjoyed this session, and now we can open up for questions.